So we have now expressed a linear regression with one predictor this way, that if you tell me the x value, then I model that the outcome variable is an independent draw from a normal distribution centered at beta 0 plus beta 1 xi with variance sigma squared, and the sigma squared does not depend on what the x is. That's linear regression. So what we're going to talk about now is parameter estimation. In other words, how do you use your data to estimate the parameters of this model? And I'm going to restrict myself to simple linear regression here. Simple linear regression just means, this word simple just means one predictor. The reason I'm restricting myself to one predictor is that in order to have this discussion in a precise way for more than one predictor, you would want to use linear algebra, and I'm not assuming that for this class. But please know that that is the case, that you can certainly extend all these things for multiple predictors. In fact, you will run regressions for multiple predictors in this class. I'm just not going to explicitly write down the expressions for the parameter estimates in math. And if you're interested, Stat 318 teaches those concepts, because that course does require linear algebra, Math 206. So let's look at this model. What are the parameters? And I won't pause here and ask you to write it down in a survey, but I do want you to think about it. What are the parameters? Well, I see an intercept and a slope that I would need to estimate in order to know where my line falls, right? You need the intercept and slope to estimate the line. But I see a third parameter. I also see this variance. That's a parameter too, right? How much do the y values vary within each subgroup based on x is something I need to figure out if I want to be able to actually describe the relationship between x and y. So those are my estimands, quantities of interest. Estimands, also known as parameters. Sigma squared, beta naught, which is the intercept, and beta 1, which is the slope. So we're going to have to come up with estimators for those parameters. Now, remember, I'm going to write something down, I'm going to erase it quickly. Earlier, we were trying to estimate mu, and so we did it with y bar, right? Earlier, we were trying to estimate sigma squared, and so we did it with s squared. Right, so you're already familiar with the idea that we could list some estimands, some unknown parameters, and then use the data to try to estimate them. So that's what we're doing here. How are we going to estimate sigma squared? Well, with a quantity that we're going to call sigma hat squared. How will we estimate beta 0 or beta naught? With a quantity we'll call beta naught hat. And we'll estimate beta 1 with a quantity we'll call beta 1 hat. So I think you see the pattern here. When we put the hat on the parameter, that means we're talking about an estimate of that parameter using the data, something akin to x bar in a simpler case. When we don't put the hat on, we're talking about the true population quantity, something akin to mu in a simpler case. So here's how we're going to do this. I'm going to do this a little bit backwards on purpose. I'm first going to talk to you about how to estimate sigma squared, assuming that you already have estimates for the intercept and slope. Then I'm going to talk to you about how you might estimate the intercept, assuming you already have an estimate of the slope, and then we'll spend a bunch of time thinking about how you would estimate the slope itself, because that's the most important quantity, because that's the one that relates the most to the relationship between x and y. So here's what we're going to do to estimate the residual variance. So let's draw a picture. Here's x, and here's y. And the data might look like this, making it up, okay? And we're going to assume we already have estimated the intercept and slope, which means that I already have a line that I can draw, right? This is a line with intercept beta naught hat and slope beta 1 hat. Okay, so here's what I'm going to do. I'm trying to figure out the residual variance. In other words, choose any value of x. For that value of x, the corresponding y value should follow a normal distribution around the point on the line that corresponds to that x. And then the thing I'm trying to estimate is what is the variance of that normal distribution. So how are we going to do that? Well, think about drawing a vertical line from each point to the regression line. Okay, that's what I'm trying to do here. Draw a vertical line from each point to the regression line. That vertical line represents the residual, right? We said that the residual is the difference between the actual Y value of the data point and what the line predicts or what the model predicts for that data point. So just like we did in simpler examples, to estimate the overall variance, we're going to see how far each data point is from its predicted mean, square those quantities, add them up, and divide by something sort of like the number of data points. In other words, sigma hat squared is equal to, take the first data point, subtract, there's the first data point, subtract the mean Y for that data point's X. What is it? Well, it's the estimated intercept plus the estimated slope times the first data point's X value. So what I've written so far is the residual for this first data point. Again, it's the actual Y value, right? Minus the Y value predicted by the line for that corresponding X. I'm going to take that quantity, I'm going to square it. I'm going to calculate that same quantity for all the data points. So I'll write it all the way up to the last data point. There's the nth data point, right? Subtract the actual Y value of the nth data point minus the intercept plus the slope times the nth value of the predictor, square those and add them all up. That's called the sum of squared residuals, and that's a term you'll hear a lot more as we go forward. I'm going to divide this quantity sort of by the sample size, but I'm actually going to divide it by the sample size minus 2. Now, if you remember, when I was using S squared to estimate sigma squared, in a simpler case, I had n minus 1. Now I have n minus 2. What's going on here? Well, notice that I've already estimated 2 things before I got to the point where I could estimate sigma squared. What are the 2 things? Intercept and slope. So I used up 2 pieces of information already. I have less information left here. So this is the degrees of freedom, right? It's a term we've now heard before, degrees of freedom. And the idea is we used up 2 pieces of information. I'll kind of put that in quotes, to estimate the line, to estimate the intercept and slope. Now, I don't mean to imply that pieces of information is a technical term. If you want to see exactly why we need to be dividing by something other than just the sample size, take a look at those optional videos that I posted previously when we were trying to show that that on average S squared was equal to sigma squared in the simpler case, and something parallel is going on here. You need to subtract the number of parameters you've already estimated in order to get the degrees of freedom, also called the denominator, for this estimate. So, okay, that's the degrees of freedom. But big picture, what are we trying to do? We're trying to estimate the residual variance. And what I'm telling you is that the way to do that is to take each data point's Y value, subtract the prediction that the line gives for that data point, square those residuals, add them up, and basically divide by how many there are, but really divide by how many there are minus 2. Just to introduce a little bit of notation, here's a more concise way to write the same thing. More concise way to write this. I'm going to introduce this piece of notation, yi with a hat on it. That is called a fitted value. What is the fitted value for a particular data point? Well, it's just exactly the point predicted by the line. So if you have a data point where X is equal to 3, how am I going to find a fitted value for that data point? Well, here's 3, and there's my fitted value, right? So it's intercept plus slope times, or estimated intercept plus estimated slope times the X value gives you the fitted value. So now that we have that, right, then we're back to this thing. Remember, this is our residual variance estimate. And that is equal to, I'm just rewriting what we have above, 1 over n minus 2 times the sum over all the data points of the actual Y value minus the fitted Y value squared. So take a moment if you need to and compare this to what we have above. These are the same thing, but usually people would write the residual variance estimate this way because it's more concise, but it's the same thing. Okay, so we have accomplished 1/3 of our goal. We've talked about how you would actually use a data set to estimate one of the parameters, in particular sigma squared, but only if you've already estimated the intercept and slope. So now, what if we're trying to estimate the intercept, assuming you've already estimated the slope. So you already have beta 1 hat. Here's the idea. We have some data that fits into an XY plane here. If you look only at the X values, there will be some sample mean for those X values, right? Like there'll be some value X bar that's kind of in the middle. And if you look only at the Y values, there'll be some sample mean Y bar, right? And those 2 points, of course, have an intersection. So this right here is the point with coordinates X bar, comma, Y bar, okay? The idea here is that you want the regression line to go through the intersection of those sample means. Why? Because that means it's right in the middle of your data, right? So you want to come up with a regression line that's going to go through those that intersection of the means. So to find the intercept, you note that if the line goes through the intersection of the means, it also has to go through the intercept itself. So here's the intercept, right? And so this intercept is at the point 0, beta naught hat, right? That's the definition of an intercept. X is equal to 0, Y is equal to intercept. So the regression line is going to be the line that connects these things, okay? And so the slope then, the slope estimate, because we're talking about what we actually calculate from the data, can be calculated based on these 2 data points, right? If I'm saying the line has to connect the intersection of the mean, of the sample means to the intercept, then the slope that I calculate from those 2 lines is going to be the change in Y. So Y bar minus beta naught hat. I'm just subtracting the Y coordinates of these 2 data points, divided by the change in X, which is X bar minus 0. I'm just subtracting the X coordinates of these 2 points. Okay, so this equation has to hold. If all I do is draw my line through these 2 points, then the estimated slope has to be equal to the difference in the Y's divided by the difference in the X's. But this equation implies that X bar times beta 1 hat is equal to Y bar minus beta naught hat, which implies that beta naught hat is equal to Y bar minus X bar times beta 1 hat. And now actually, we did it. We wrote down an expression for estimating the intercept if you've already estimated the slope. Because if you have the data set, you can calculate the sample mean of X and the sample mean of Y. And if I've already estimated the slope, now you can figure out what the intercept must be. So I think hopefully you can see here why we're going to spend most of our time focusing on how to estimate the slope, because once you have the slope, taking your estimate of the slope and putting that together with an idea that you want the line to go through the intersection of the means automatically implies a value for the intercept.